last time we talked about one example of gapless matter that is superfluid. So today we are going to describe another type of behavior of a quantum system at low temperature that is called Fermi liquid, and we will see that Fermi liquid is a much more complicated thing and maybe much more interesting thing to study, but also present challenge for quantum field theory. So Fermi liquid, the theory of Fermi liquid is linked to the name of Landau. Landau was the first to propose the notion of the theory of Fermi liquid, and we are going to start by describing Landau's theory. So my task is made easier because Subir already gave you a sketch of the theory. I want to go a little bit into more details of how to use the theory to compute correlation function today. Okay, so let's start with a system of free fermions. So free fermion would be a very easy thing, should be an easy thing to describe. We know that for free fermion, if we put, so for simplicity, I'm going to ignore the spin degree of freedom, but if one can put it in, it will complicate, it will make formulas a little bit more complicated. I'm going to assume spinless fermions and put them at 0 temperature. So I have some fermions, and at 0 temperature, and I assume also for definiteness that my dispersion relation for the fermion is p squared over 2m. In fact, most of the things that I will be talking about will not depends very much on the precise form of the distribution function. For application, I have in mind helium-3. It's one of the quantum liquid that is a fermion, is a Fermi liquid over large range. But strictly speaking, helium-3 is not a Fermi liquid at very low temperature. We know that if we take helium-3 and take temperature exactly to be equal to 0, then it will be a superfluid because of the Cooper pairing between the fermion. But in quite a large range of temperature, it is a Fermi liquid. So I'm going to ignore pairing and then consider helium-3 as a Fermi liquid. Another example of a system that one can hope to describe is electron gas in metal. Okay, so if we ignore the interaction between the fermion, then the ground state is just a field Fermi sphere. So here I have px, py. You should mentally draw another axis pz if one is describing a three-dimensional Fermi system. So that's the ground state of the system. And for free fermions, we know in principle, we can compute everything. So for example, if we want to compute the correlation function of density, and it's 0, 0, right? And usually we would put a time order, if we want to compute the time order 2-point Green function, we can follow the standard rule of Green's function technique. So this quantity will be equal to schematically computing this loop diagram, okay, where the insertion here is a vertex corresponding to the density. So here, if the fermion field is psi, then this vertex, each of these vertex is just associated with number 1 because the vertex is just psi decker psi. And then the fermion propagator here can be read out from the Lagrangian, which is simply I psi dagger I dt plus grad square over 2n psi, and the propagator here is I divided by omega plus minus epsilon p, and here I would have I divided by omega. Let's see. Let me use quasi-relativistic notation and denote the energy as P0. So here I have P0. Here I have P0 plus Q0 minus epsilon P plus Q. And here Q and Q0 is just the momentum of the incoming that's coming into the diagram. So comparing this diagram, one find the Fourier transform of the two-point function of the density. Okay, so the result, I'm not going to write it down, but the result would be something like this. I'm going to write it in an integral form. You find something that looks like integral of dp p dot vq divided by omega minus p dot vq. Maybe I'm actually q. Here is q, q naught, q vp, p, and then I have here a delta function. Let me, maybe it's not a good place to, let me just write dot 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 here. I'm not sure if I get everything correctly, but I just want to tell you that this calculation is just a standard field theoretical calculation using Feynman diagram. Everybody who has not done this calculation once in their life should do that after this lecture. Yeah, every theorist should compute a one loop graph at least once in their life, and this is a nice one loop graph to compute. Okay, but if that was the contents of Landau theory, then there's nothing more to say, right? We just do Feynman diagram and we get all the result that we want. But as we learned from the last time, on the example of helium-4, a lot of condensed matter system that we are interested in the real life is not described by free field theory. They are not even described by a weakly coupled field theory. Typically, the coupling constant, the interaction between the atoms in a quantum liquid is strong. An example is helium-3, for example. If you look at the density of helium-3, you see that the distance between the atoms is of the same order of magnitude as the range of the interaction. And moreover, the interaction energy between the atoms of helium-3 is of the same order of magnitude as the kinetic energy that one would estimate based on the uncertainty principle. Yeah. Yeah, for example, we can do any space-time dimension. Here is this integral will depend, the integral will be taken over d dimension, d is the number of spatial dimensions. Yes, so one plus one dimension. I'm going to talk about any spatial dimension. In one plus one dimension, the situation will be very interesting, and maybe we will talk about that later. What happened in one plus one dimension later on. But in system that I want to talk about are 2+1 or 3+1 dimension. Yeah. So the questions is how to describe Fermi liquid with strong interaction between the, say, electrons in a metal, or is also one example, such example. If you compute the kinetic energy and the potential energy between electrons in the metal, you find that both of them are given parametrically by the Rydberg energy scale. There is no small parameter that one can choose, that one can dial in metal to control perturbative expansion. The exception to this rule is only in matter inside white dwarf. If you compress matter to a very high density, then you'll find that becomes more and more, less and less strongly coupled. So when you have when you have a system of electron interacting with Coulomb interaction, then the larger the density, the better for perturbation theory. But in metal, that parameter is about 1. This happened because the energy, the kinetic energy. So if we have a gas of electrons with density n equal n divided by v, and let me denote the distance between neighboring electrons to be a. So a is equal 1 over n to the power 1/3, right? Then the kinetic energy, typical kinetic energy of an electron is determined by the Fermi energy, or roughly speaking, by the uncertainty principle, each because of Pauli exclusion principle. The minimum momentum of each electron is 1 over a. The kinetic energy is then 1 over m a square, right? And the potential energy that one electron exerts on the other is of order e square over a. And so when a is much larger, when a goes to 0, this kinetic energy is much larger than the potential energy. These are of the same order of magnitude when a is of the same, when a is equal to the Bohr radius. And so in a metal, the distance between electrons is typically the Bohr radius. And that's why k and v is of the same order of magnitude. Yeah. How to describe Fermi liquid with strong interaction? It looks like the problem is hopeless. Actually, if you look at the Feynman diagram, it's very complicated to compute. In the 1950s, people tried different technique to resum perturbation diagram. Then came Landau and said that actually the problem can be solved. And the first observation, crucial observation by Landau is that even when the interaction between the electrons is strong, when we go to very low energies, the quasi-particles, the electron becomes quasi-particle that are weakly interacting. So Subir have given you one of the arguments. It's actually the original Landau's argument on why it's happened. If you have a quasi-particle near the Fermi surface, it would decay to so I write here E should be thought of as a quasi-electron, electron plus some stuff surrounding it to make out of quasi-particles. It decays into another quasi-particle and a particle and a hole pair. And because this the energy and momentum has to be conserved during this decay process, the amplitude of the decay may be large, but the phase space of such a decay is small. And so Subir have shown you how to compute this decay rate, and one find that the particle decay width goes like epsilon square. If the energy is epsilon, the width is even goes to 0 even faster, it's epsilon square. And so first notion is that quasi-particle becomes long-lived at low energies, and one then should be building an effective theory describing this strongly interacting system in terms of the quasi-particle, in the language of which the description becomes simpler. So let me describe to you first how free Fermi gas is described in Landau's language, and then we generalize it to the case when there is interaction. Okay, so free Fermi gas is very simple. In Landau's, we have to recast this calculation in a slightly different form. So free Fermi gas is described by the distribution function f as a function of x and p. So here is the one step that one has to make is to instead of describing the system in terms of the electrons, we now go into a description in terms of the distribution function of the electrons in phase space x and p, and write down the equation, the differential equation, the Liouville equations that govern the evolution of the distribution function as a function of time. df over dx plus d over dp epsilon of p df over dx plus this minus d epsilon p. And here I'm going to write something like this: a plus v of p cross b df over dp equal to 0. Okay, so what is going on here? Here I'm writing down a Liouville equations as if particles that we are describing can be thought of as a swarm of classical particles in phase space. That's the picture one might have. We have some region in phase space. We put in particle. Each particle is occupying a place in x and p, and f counts how many particles is in the volume of phase space. And then this would be the classical equation that called the Liouville equation that describes the evolution of the distribution function. Here, the epsilon over dp is nothing but just the velocity of the motion of the particle. And here I write p dot. P dot would be 0 if the system is free, but we put in order to compute this Green's function, we put in the external electric and magnetic field, and this would be the p dot, the E plus Vp, the Lorentz force acting on the particle, equal to 0. Any question so far? No? So now I'm going to show you how to use this to compute the two-point function. To compute two-point function, we need to appeal to linear response theory. In order to compute the two-point function of the density, for example, we turn on a source coupled to the density and then measure the density at a later time. Right? So the source coupled to the density is the scalar potential A0. So we turn on in the Lagrangian A0 times n. Okay, and that's equivalent to turning on an electric field equal minus gradient of A0, as we know. And then we measure the density at a later time. Okay, so the density So how do we use the kinetic equation to solve this problem? We need to solve the kinetic equation in external electric field to linear order in the deviation from the ground state. So we write F equal F0 plus delta F, where F0 is the theta function governing the giving us the this field Fermi sphere, the ground state at 0 temperature. Put that into the equation above. We find d delta F over d T plus, and then here I'm going to write V of P, that the epsilon of P over dP, I call that V of P, dot d delta F over dx. And then I have the electric field plus E dot dF over dP. But here electric field is considered as a small perturbation. In linear response theory, I have to write dF0 divided by dP is equal to 0. Okay, so now this is a linear equation that one can solve very easily. And one way to do that is to go to Fourier components and write delta F in the Fourier component of delta F in terms of the Fourier components of electric field. And you can, again, this is an exercise that everybody can do. I encourage people to do this exercise. And after we find delta F as some linear function times the electric field, and that depends both on frequency and on P, we put that into the expression for the density, which is equal to integral over all momentum of the distribution function x and p. The density depends only on x. That includes both time and space. But the distribution function depends on x and p. We integrate the deviation of the distribution function from the equilibrium, get delta n, and that gives us the 2-point functions. Roughly speaking, the result should be the convolution of the 2-point function of the density that we are searching for and the external perturbation of A0. Now that's a scheme how this calculation is done. And we would observe that these calculations reproduce exactly the result that we get by computing this one loop diagram. Okay, so this is demonstration that one can use the kinetic equation to obtain the result that normally we would compute loop diagrams. The difference you can see here, there's one thing that I want to emphasize. You get from this result reproduce the result from the loop diagram only in the long wavelength limit. That is the limit when the frequency of the external perturbation is much smaller than the Fermi energy, and the momentum of the external perturbation is much less than the Fermi momentum. Okay. The loop diagram gives you the whole dependence of the 2-point function at all energy and momentum. The kinetic equations, this Liouville equation, gives you the correct result only in the long wavelength limit. Okay, now Landau's theory of interacting system. This also has been mentioned by Subir. It's the most prescient insight of Landau is that one can generalize this formalism to include interaction between the particles. So for interacting system, Landau declared that what we have to modify the equation, there is only one thing that we have to modify in our equation. That is, we need to make the energy of a quasi-particle with momentum p at point x to depend on the deviation of the distribution function at other momenta. So let me write this formula out. Epsilon p of 0 plus integral over all other momenta, let's call that dp prime. Some functions f that depends on two momenta, and then delta f as a function of x and p prime. Okay. So Subir has given you a way to look at this function f. Roughly speaking, it describes the forward scattering if the particle with momentum p with another particle momentum p prime. It's only it's as if the presence of a particle with momentum p prime changes the energy of particle with momentum p. But here, this change happened at the same point. That is, we assume that interaction is short range. Coulomb interaction would also fall to this category because Coulomb interaction is green. And so this function in long wavelength approximation, the response, this response function, this function f is local in space, but it's non-local in momentum space. It's a function of p and p prime. Okay. And the equation, the Landau kinetic equation becomes a generalized Liouville equation that I'm going to write this form. The only new term in the equation is this d epsilon over dx. So if you think about epsilon as the energy of a particle, one can think about that also as a Hamiltonian that describes the motion of the particle in phase space. And this would be x dot, and that would be p dot. P dot would be non-zero, even in the absence of external field, because the Hamiltonians of a single particle can depend on space through this delta f here. Okay, so any questions so far? Yes. How the quasi-particle is fermion is expressed here. So here we the fermion the fermion distribution function has to be limited from 0 to 1. So that's one thing. I'm going to actually later on make even a stronger limit on the function f. Namely, this function f has to be either 0 or 1. That would be the way to encode this information. In fact, there is a certain now we are very used to this equation, but in the beginning it was not obvious that one can describe a quantum system in terms of a classical distribution function like this. In fact, there was I read recently an interview of Celine, who was the person who first thinking of, you can find in 2 papers, Landau wrote 2 papers, and in the second paper, most of the citation of the second paper on Landau Fermi liquid theory are on paper by Celine. And Celine claimed that it was him who convinced Landau that there is this notion of a distribution function of a quantum particle actually is something that makes sense. Yeah. Yeah. Can the semi-classical treatment capture the parallel The chiral anomaly has to be it has to so the answer is yes. In order to do that, one has to write, instead of x and p that have this form, we have to add in x dot and p dot the anomalous term. So the anomalous term would appear in the anomalous. There's a anomalous velocity. You can add here the anomalous velocity. We can modify the equation appropriately, taking into account the Berry phase of the spin 1/2 particle. Then we can reproduce the chiral anomaly.
And you're neglecting the collision integral.
So here I'm going to specify what the regime of where I'm going to apply this equation for. So I'm going to use these equations to compute things like 2-point Green functions at momentum and frequency both going to 0. Okay, so both are smaller than the Fermi energy and Fermi momentum, but taking the limit when omega over q is fixed. So they are going to 0 at the same rate. And now, in this case, I think one can argue that the decay of the collision gives rise to the decay of the quasi-particle. That rate of decay, as Subir mentioned, is of order energy square. So if I'm sticking to this this limit, this very restricted limit, then one doesn't have to take into account the collision between the quasi-particle. Okay, so so it's unclear actually. It's not obvious, let me say that this equation would be the one that encapsulates the low energy dynamics of an interacting fermionic system. And I'm sorry?
What's Vp here?
Vp is equal to d epsilon p over dp. So epsilon of p is equal to this one. In the no, Vp it's linear, because in the free case, this one is just d epsilon over dp. So for particle with quadratic dispersion, it's just p divided by m. Yeah. So in the non-linear case, that Vp in principle would contains also information about the this part of the distribution function. Okay, so here Landau proposed this as a description of fermionic system, interacting fermionic system around 1957, 1958, and applied it to helium-3 and get various consequences for helium-3. This equation, how do we use this equation? In order to compute linear response, we turn on external magnetic field, electromagnetic field, measure the density, and then read out from the linear response formula the 2-point functions. One can, for helium-3, we have to put in spin of the helium-3 atoms instead of one function. F here we would have a function that is singlet and the triplet functions depending on the spin. Now it looks like one may be concerned that we need to, in order to make prediction, we need to know infinite number of parameters, which is a function of 2 variables, p and p prime. But in fact, because of rotational invariance, this function is only a function of the function of the angle between the two p. The absolute value of 2p can also be set on the Fermi surface, because most of the action, if this equation, as we will see, happen near the Fermi surface. So instead of a function of two variables, in fact, here we have a function of a single angle between p and p prime. And one can decompose this function in spherical harmonics. And it turned out that in helium, only a few first one are differ from zero on this F. Two of the, roughly speaking, the zeroth and the first harmonics are substantially different from zero. Okay, so how people how are we sure that this is the equation that describe interacting fermionic system? So first, we can compare the prediction of the theory to experiment done in helium-3. Second, we can compare the prediction of this theory to perturbation of this kinetic equation to perturbation theory. So this is what is done in the book of Abrikosov, Karkov, Telashinsky in the first 4 chapters, about 200 pages. One can read how a resummation of perturbation theory to all ordering perturbation theory can reproduce the predictions of Landau's Fermi liquid theory. So roughly speaking, the diagram that one has to compute looks like this kind of diagram. So in order to compute two-point function of density in an interacting system, we have to take into account interaction between the electrons. Yes, this blob is denote complicated set of diagrams that describe interaction between the electrons. And there is a precise relationship between these Landau functions to the 4-point vertex function in the diagrammatic expansion. This is not at all trivial. There's you have to really read. We have to really, well, let me just sketch. This function is equal to, this function gamma is equal to a sum of an infinite number of graphs. Okay, so here I'm drawing a schematic description where the vertex here is two particle irreducible 4-point vertex computed in a certain limit of momenta and omega and k. You have to take the appropriate omega over k equal to 0, I think. No, k over omega goes to 0 limit, and then sum this diagram up with a certain kernel, two-particle kernel, that is the singular part of the particle bubble. Okay, so most of this is very technical, but one then at the end reproduce, for example, prediction of Landau's Fermi liquid theory, right? Zero sound, magnetic susceptibility of helium-4. Okay. Okay, so now I'm going. So any questions so far? So in principle, Landau Fermi liquid theory can be used also, not only to compute two-point function, but also to compute nonlinear response. For example, in order to compute three-point function of density, then we would solve this kinetic equation, not to linear order, but to next to linear order, right? Delta n of the order E square, electric field square. And then the kernel that one obtained would be the three-point function, n, three-point function. And that can be done to all order. The claim that I think I'm going to make, I'm not sure if it has been shown rigorously in perturbation theory, is that this kinetic equation can be used to compute any point functions of density in the limit, in a similar limit, when all the frequency and momenta of the external legs goes to 0 at the same rate. It's in the scaling limit when you take all the q and the omega goes to 0, keeping the ratio between the omega and q fixed and the angle between the momenta fixed. Okay. It's too constant. Yeah, if the constant is fixed. Okay. Okay, so any question so far? Now let me tell you why we want to understand better, why even having a formalism from Landau to compute response functions in interacting fermionic theory still give us some sense of something here that is not really satisfactory. And let me articulate this feeling that I think many of the of condensed matter physicists have. The framework that we use to understand low energy dynamics of quantum system is effective field theory. Okay, so effective field theory is something that allows us to zoom in into low energy physics, forget about all the high energy physics. The high energy physics is only used as an input to fix the coefficient, some phenomenological coefficient in the low energy theory. And knowing the low energy theory, we can compute things without thinking about the microscopic UV. From this point of view, Landau's theory seems to be the ideal example of a low energy effective theory. Right? You can just know this, there is only this input. The only input we need to have is this function epsilon 0 of p and the function, the Landau interaction function. And after knowing that, we get all the results that we want. But this is not effective field theory. Well, usually when we think about an effective field theory, we have in mind a certain very classic framework that is laid down by Weinberg in 1979 in a paper called Phenomenological Lagrangians. So when Weinberg wrote this paper, what he's managed to accomplish is to make sense of the effective Lagrangian that is used to describe pions in quantum electrodynamics. So this Lagrangian is not renormalizable. There are terms that, there is infinite number of terms that have growing dimensions, but one can have a procedure that allows us to compute Green's function not only to leading order, but also to the next leading order in an expansion parameter, which is the momentum. So it's momentum becomes the expansion parameter in Weinberg's effective field theory. This theory that Landau wrote down is just one theory, and it's unclear how one can improve it. Weinberg's effective Lagrangian for pions, in principle, can be improved to infinity. One can write out an infinite number of counterterms, compute scattering amplitude between pions to arbitrary power in momentum. So not only we need to compute loop graph, and then also take into account the extra term with higher and higher derivative. But there is a procedure to systematically improve our prediction. Landau's Fermi liquid theory gives us the leading order result, but doesn't give us a way to improve the result. That's one thing. Second, Landau's Fermi liquid theory is because it's classical theory, it gives us only prediction for certain linear response green function. So when we think about linear response green function, it's for 2-point function, it's a retarded green function. For 3-point function, it's sort of some kind of a retarded. That is, we have 2 particles here, perturb the vacuum, and then we measure the operator at a later point. If we want to compute some green function that is not linear response or response type, for example, say out of time order green function, it's not clear how Landau theory would allow us to accomplish this task. And then lastly, we don't know how to use this theory to build a theory of non-Fermi liquid. So Subir told you that one of the model of non-Fermi liquid is a Fermi surface, fermionic system coupled to a massless bosonic field, which could be a massless scalar field with its mass dial to criticality, or Fermi surface coupled to, say, a U1 gauge field. So if we had usually what we would do in quantum field theory is to write down a theory describing this Fermi surface and then turn on interaction with the external, with the electromagnetic potential, make that electromagnetic field dynamical, and then we'll go from there. Okay, here we have a situation, we have the starting point, that is before coupling to electromagnetism, or after coupling to background electromagnetism, is described not in terms of Lagrangian, but in terms of a kinetic equation. And that kinetic equation, we actually don't know how to do loop diagrams or things like that with the kinetic equation. So I'm going to try to reformulate Landau's theory as a field theory with some action that give rise to this equation of motion, with the hope that this action may be later on turn out to be useful to address the problem of non-Fermi liquid. Okay, so is there any question about my criticism of Landau Fermi liquid theory? Yeah.
You mentioned that the Landau theory can't compute out of time order correlates, but you can't really do that in the power Lagrangian either, right?
We can, in principle, yeah. If you have a field theory, then I don't see any reason why we cannot, right? The field theory basically tell us all the, in order to compute a certain endpoint function, right? We have a perturbation theory to do that. We just need to do perturbation theory on a certain contour. Yeah. So the leading order would be to take the leading order Lagrangian of chiral perturbation theory, and then do, say, weak rule to reduce 4-point function to 2-point function, and then take into account the interaction vertex. So all the calculation can be done just using standard rule of Green. So the path integral can be used with any contour. Just the usual contour of Feynman is the contour that go from 0 to infinity. That's the one would get the Feynman rules, with green function being the Feynman green function. But one can also do it in the Schwinger-Keldysh contour. So yeah, I don't know from your side it's like that, one of these. And then, yeah, I don't see any problem using standard effective field theory like Weinberg type to compute out of time green function. But using a kinetic Liouville equation it doesn't seem to be the right formalism to do this kind of calculation. Okay, so now I'm going to tell you how one can use a method that we have developed recently, and these are the references that where you can read. Called the COA join, the method based on the technique of COA join orbit to reformulate Landau Fermi liquid theory as a field theory. Sheila? Oh, so left-hand side? Left-hand side is this function f, actually. Yeah, let's say this function f is equal to a certain, I'm not going to write that.
What is wrong with that way of doing it? Like there is, it seems like there is a Lagrangian and you can see value corrections there also.
Yeah, you have to, in order to compute a certain two-point function, you have to sum up an infinite number of Feynman diagrams and analyze very carefully the infrared behavior of the individual diagrams. So that's, in principle, I think that can be done. It has been done in HED only for the, I think, for two-point function of current. Yeah. Okay, so now let me tell you the basic idea what we want to what.
We have just differential equation. Is there a sense in which there are higher order corrections in the limits that we expected?
Yeah, there is a sense. That is this.
Can it be characterized exactly what kind of terms can be added and then matching them with experiment?
It's not. It's hard to be sure that we list all the terms. So here we can, for example, say that what we are missing here are, for example, derivative terms that give us the energy as not just a function of delta F, but also derivative of delta F. But we are not never sure that we are exhausting all the possible derivative correction, because there is no straightforward rules how to list all the correction. Okay, so let me make one remark about the kinetic equations. So the kinetic equations that we wrote down here is essentially a classical equation. It could be thought of as a Liouville equation describing the motion of each individual particles in phase space. Right? Its equation basically tells us that there are well, we can interpret that. It's not a correct interpretation, but we can interpret that equation as a classical equation describing a classical system of point-like particles in phase space, each of which move along a certain orbit, and this is a Lagrangian description of the density at a point. When we view this equation this way, it's clear that due to the conservation of phase space, the distribution function is constant along the motion of each individual particles. If we have a finite volume and we follow it in evolution, the number of particles inside this small volume remains the same. The volume is also remains the same because of the conservation of phase space. And so if we start our evolution with a state with a sharp Fermi surface, F equal to 1 inside and 0 outside, and evolve it with time, then the function would still have the form of it being either 1 or 0. The form of the Fermi region can change with time, but the function will always be 0 or 1. Okay, so what I said is that Landau equation can be thought of as an equation that evolved that govern the evolution of a shape of a surface. So let's draw this picture here. So I'm going to draw only two-dimensional picture of the phase space of a 1 + 1 dimensional system. But you have to imagine that this x stay for all x1, x2, x3, and this p stay for p1, p2, p3. Okay, so let's imagine that we have a system that we start at -infinity in the ground state. So ground state means that we feel a Fermi surface. So here it's in one dimension, the Fermi sphere is just an interval. We fill this region with electrons in phase space, f equal to 1 and f equal to 0 outside, okay? And subject the system to external electromagnetic field, E and B field, arbitrary field. Okay, so after some time, we will see a different system that has a different shape of the Fermi surface. But the basic feature that f is equal to 1 inside, f equal to 0 outside, still must remain. Okay, so we want to, ideally what we want to do is to write down a theory that can describe how this surface changes and responds to an external electromagnetic perturbation. Okay, the goal is to reformulate Landau's theory is a theory of surfaces of the shape of the Fermi surface. Okay, so Fermi surface can have shape that here is not clear, but each of these at each x, the Fermi surface can be not round, not spherical, can have a different shape, and the shape of the Fermi surface can change in x. Okay, so that's our task. Okay, so what we know from Landau is the energy. So we can think about this Landau functional as a functional that gives us the total energy of a system with distribution function different from the ground state distribution function. So the Hamiltonian can be thought of as integral of epsilon p0 delta f. So h is equal to some constant, say E0 plus delta, so let me see, delta dp dx epsilon 0 of p delta f x in p plus 1/2 integral dx dp prime f p prime delta f xp delta f xp prime plus ... and what stays in, so this is, you can think about this as h as a functional of f, and the energy of a single particle in Landau kinetic equation can be thought of as the variation of the Hamiltonian with respect to change in the distribution function f at x in p. So in principle, so here I can imagine that what Landau wrote down is an expansion of the energy in powers of the deviation from equilibrium. And Landau truncated this series to quadratic order, but in principle, this series should goes further, cubic order, quartic order. So plus in principle, one can imagine answering Nati's question, terms higher order in derivative, also derivative of f, etc. So this Hamiltonian, in principle, improving the Hamiltonian presents no problem. This Hamiltonian is the conserved energy in the system. I'm sorry?
The only considered constants equal to density, not other set.
That is Landau's postulate that is verified by perturbative all order in perturbation theory calculation. Yes. Only this is important, nothing else in a Fermi liquid with short range interaction. But with the Hamiltonian, we don't know how to, a priori, we don't know how to write down the equation of motion. In order to have an equation of motion of a classical system, we need the Hamiltonian and a symplectic form in phase space. So let me explain what does it mean. So we want to write down, so the form of the Landau's kinetic equation is an equation that can involve first time derivative in, it's not a wave equation with second derivative in time, it's equation at first time derivatives. So if we want to describe a system of, say, some degrees of freedom, C, some kind of C, some degree of freedom. Say, let me put an index A there. A classical system for which the equation of motion is first order in C typically has an action that contains two terms. One term is the terms that have a form of A C A dot, okay? And another term is the Hamiltonian. Let's see. For example, a spin in a magnetic field is described by such a Hamiltonian, where this A is a gauge potential that encode the information about the non-zero commutation relation between the spin. Okay, so this A, one can think about this first term also in the following way. If we have a spin in a magnetic field, the first term gives us the Berry phase of a spin when its direction changes in space. In space, right? So this can be thought of as the Berry phase in the quantum theory. And this is just the energy of system. But sometimes it's good to have both classical and quantum, though all that I'm going to tell you are like the classical action interpretation of classical equation of motion, like the equation of motion for spin can be obtained from this diagram by just doing a variational calculation. But sometimes it's good to have in mind quantum interpretation of term, especially term with first order derivative in the reaction. Any question so far?
Constraint of the depth boards and extra integrated balancing.
How is the
Constraint even if you depth remains at the bottom
has reflect in the formalism that I'm going to build? So it's here I'm writing a very schematic form of the theory that I want to have. This C is going to be parameter that parameterizes the shape of the Fermi surface. So there's an infinite number of parameter C here. That is some kind of a shape in the Fermi surface. and this H, that is something we know. What we don't know is how to write down a term with first time derivative in the shape of the Fermi surface. Okay, so this in the usual quantum mechanics, right? When Xi is P and X, this term would be Px dot kind of term. So it's Px dot is the term that gives us the commutation relation between P and X, right? And the if one take this Lagrangian and then go to the Hamiltonian formulation, we will find that the commutation relation between psi A and psi B, more precisely, this theory corresponds to a Hamiltonian system given by this Hamiltonian, and the Poisson bracket between omega A and B be equal to the inverse of the field strength that one built from this A, interpreting A as the potential, like a Berry phase. This FAB would be Berry curvature, minus 1 would be the commutation relation between the two. This C. Okay, so this is something that we want to have in our theory. That's the, roughly speaking, we're asking the following question. We have a Fermi surface, a ground state. But imagine that we turn on some perturbation to change the shape of the Fermi surface. When the Fermi surface changes its shape, what is the Berry phase that is associated with the variation of the shape of the Fermi surface in time? So that's the question that we want to address. Okay, any question so far? Yeah. Roughly speaking. Yeah.
What does it depend on?
So if one thinks very straightforwardly, in a Fermi surface, what we want to describe is shape perturbation. Then the first most straightforward things that we would think about would be a height function. So we have a Fermi surface, and we want, say, in 2 + 1 dimension. Perturbing a Fermi surface would correspond to shifting the position of the Fermi surface by a function h, which is a function now of h, xt, and theta. Theta is the angle in momentum space. So roughly speaking, we want to write down some action which involve symplectic form in the space of this height function, h.
So
this is Xi. This is our Xi.
And what is A? Index A?
This A is this, or this T, well, sorry. X and theta are A.
And the dimensionality of X is the dimension. So imagine we're in 2 dimensions.
Mm-hmm.
Is it 2 vector or 1 vector?
X would be a 2 vector in 2 + 1 dimension.
So in addition to time, we have three parameters.
Three parameters. In 3 dimension would be 5 parameters, because we have a sphere, 2 coordinates on the sphere, and 3 spatial coordinates.
But that's not what we normally do in field theory. These are functions of space.
These are functions of space. This is not really normally what we do in field theory. Here that would be something that we normally would do in quantum mechanics.
Why is there mass dependence? Because Fermi surface is there's one surface.
One surface, but imagine that we follow Landau's kinetic equation, perturb the system with electromagnetic field that depends on space. Then the electron will move from one place to the other, right? And at some point in space, the density is larger, some point smaller. So even the volume of the Fermi surface here would be larger, here is smaller. So And also the shape might be different. If you have an electric field, the electron may shift in momentum all in one direction in one place. If the electric field point in the x direction, to another place if the electric field there is pointing in the opposite direction. So the Fermi surface is really a codimension 1 surface in phase space. Codimension 1 surface in phase space. That's that the.
So this is not a Fermi surface of the entire system. It's the Fermi surface of a small region here and there.
No, this is how Landau taught us to describe such a system. We have a distribution function. That is a function of phase space. So in fixed x, if I fix x, take a slice in phase space in fixed x. As a function of p, the distribution function is 1 inside a certain surface and 0 outside. Right? The most, that's the claim is the following, that the Landau Fermi liquid theory is some kind of field theory formulated in terms of infinite number of parameters, infinite number of fields, because there's this theta, infinite number of fields that depends on the, we can think about that as an infinite number of fields depending on the angle on the Fermi surface. Next time we are going to build a formalism that allows us to efficiently parameterize the low energy degrees of freedom of a Fermi liquid, which is the shape of the Fermi surface. And this is where we have to talk about the group of canonical transformation and the coadjoint orbit of the group of canonical transformation. That turned out to be the most convenient language. Yeah. Thank you.
So the kinetic equation that you wrote down, that depends on the existence of solid particles in the system. So, but you can generalize that and work in non-equilibrium, so you have a quantum Newton equation, quantum transfer equation that you can get from the clouded. So will the action that you construct, can it be applied to that general transfer equation also?
I'm not sure if it answers I don't know the quantum Boltzmann equation well enough, but there is a frequency. Yeah, there is a frequency, and I'm not sure how to deal with this frequency dependence.
If you have lunch, maybe we could perform the